Okay, next we have Sichan again. You're already familiar to us, and now he's going to talk about Swiss.
SWiSSSE.
SWiSSSE, okay.
Yes.
Good, great.
Thank you for the introduction. Now I'm going to present to you SWiSSSE. It's a joint work by myself, Kenny, Shikha, and Bogdan. So last time I just talked to you about a more theoretical work on the security notion, and here we are going to have a construction, finally. So here the name of the paper is quite complex. You get very complex words. So let's try to break down the title of the paper a bit. In fact, in this talk, I'm going to break down the title of the paper into 3 parts. The first part is what's SSE. You have already seen part of it in the first talk, but I will take a different spin this time. Then for the second part, I'm going to describe to you what's actually system-wide security, why should we care about it. And finally, combining everything together, we are going to talk about the construction itself, the SWiSSSE. So let's get started. So it's all boring slides again. It's going to be about what's searchable encryption. Here we have a client, have a server. I'm just going to speed through all of this. The client has a kind of a set of documents. It's going to construct an inverted index that it can search over. Then this inverted index is going to be encrypted and also to the server, which then we can perform queries of the type encryption of Alice. Then the server does some computation, returns the encryption of the document identifier. So far, so good. Except that last time I said that you can just simplify everything and consider the index retrieval problem, meaning that by the end of the protocol, the server returns an encryption of the indices of the documents that match the query. But actually, it's a quite big problem. And the problem is that no one actually considers how to actually retrieve the documents. This turns out to be a quite common practice, so to speak, in the literature. So if you look at one of the most famous papers, one of the most cited papers, it has like 3,000, 4,000 citations. It says in the search functionality, in the end, it's going to return the document identifiers. And if you look at newer papers, you see the same pattern, document identifiers. And this particular paper, Dory, of course, it returns the document identifiers, but inside the paper, there's a very interesting discussion about this document retrieval part. So for that, let me read out one of the sentences inside the paper. It says, if after seeing the search results, a user decides to open and retrieve from the file system a file in the results, an attacker could infer that the file matches the query. Right, obviously it can, and that's a very big problem, which we call system-wide leakage. And this problem has been explored in a different paper called Rethinking SSE by myself, Kenny, and Shikha. So here I'm going to give you a very high-level kind of conclusion we have from that paper. And the conclusion is as follows. So we consider 2 scenarios. One scenario is that we start with those index-only schemes, those that only retrieves the document identifiers. And then we couple that with a naive document retrieval system. Think about you just store the documents encrypted in an array without duplication, nothing. And then you just retrieve the documents based on the document identifiers you have fetched in the first step. Okay, if that's what we do, then the end-to-end system is going to be vulnerable to statistical inference attacks. Those attacks can recover either the queries or the data itself. So if that approach doesn't work, what else can we do? The second approach we can do is that, okay, let's not use a naive document retrieval system. Let's use something that's actually secure. Right? We can use ORM, we can use PIR, but in the end, if we actually do that, what we end up with is a system that's actually very, very expensive. We are talking about overheads that's in the range of 3 orders of magnitude or more. So that's not practical. So in this work, what we are trying to achieve is a scheme that's actually system-wide secure and it's efficient at the same time. We implemented SWiSSSE and we show that it's actually achieved those goals. It's really efficient and that's system-wide secure. And in this talk, I'm just going to give you a high-level idea on how do you achieve those properties. So before actually describing SWiSSSE, I want to describe to you what kind of leakage we try to hide in SWiSSSE. And for that, let's start with a naive document retrieval system. So here, the boxes you see on the screen actually represents encrypted documents. And the horizontal position of them represent the addresses they are stored in. Right, so if you see two things are aligned, that means the two documents are stored in the same position. They are the same document. So the first thing we are going to consider is that we are going to make a query, Alice, and in this case, it returns the first document and the third document. Then we make another query, Bob, and it returns the third document and the last document. And here what you can see is that the third document is accessed by the first query and the second query at the same time. And this information can be learned by the adversary, the server itself. And this is exactly the leakage that's abused by a lot of attacks. And this leakage itself is called co-occurrence leakage, if you are interested. So now let's see how SWiSSSE hides that leakage. Again, we are going to start with the same set of documents, and then we are going to make the same query, Alice, on those documents. We are going to do the same thing. We are going to retrieve the first and the third document. But the difference we are going to make is that after retrieving those documents, we are going to remove those documents from the server. Okay, then, and after that, we are going to store those documents in a local stash. This stash is maintained by the client, so it's not going to be seen by the server. Okay, if this is what happens, you can see how we can make a query on Bob without revealing this co-occurrence leakage. Right? What we are going to do is that we are going to retrieve the last document as usual, but the other document, the third document, is no longer stored on the server. The client can just search over the local stash to retrieve that document. So far, so good. Except that if that's the only thing we do, we are going to end up in a situation where all of the documents will be flushed to the client stash and there's nothing that's stored on the server. And that's a very bad idea because the whole point of searchable encryption is to outsource the storage to the server. So we are going to introduce one more procedure what we call the write back. And the process, as the name suggests, is going to write back a fraction of the documents that are stored on the client stash back to the server. And crucially, instead of just flushing them back to the original addresses, we're going to flush them back to new addresses. Those addresses can be computed by the client, but they are not predictable for the server. So that's the idea. And here, let's suppose that the documents, the two documents that were originally queried using Alice, have already been flushed back to the server. Those will be new addresses, of course. And then let's make a query on Bob again. And in this case, of course, we are again going to retrieve the last document, the last black document, and then we are going to retrieve the other document that's now sitting in a new address. And here you can see that the documents that's being retrieved in the two queries no longer overlap. And that's how we eliminate this co-occurrence leakage. Yeah, that's exactly what I have described. And on the last slide, what I'm going to show you is the performance of SWiSSSE compared to plaintext database. So here what I'm going to see is just one of the parameters we have measured, and that's query response time. By that, I mean it's the time you start as soon as you make the query to the point that you generate the query tokens, make the query yourself, and retrieve the actual records. And the difference between SWiSSSE and the plaintext database is only about 1 to 2 orders of magnitude. And that's very impressive, consider that other solutions in the literature has much higher overhead. And with that, it comes to the end of my talk. If you're interested in the paper or the artifact itself, please scan the following QR codes. Thank you.
Thank you for the talk. Do we already have questions? Yes, up there.
Thanks, it was a very good talk. I wanted to ask, the solution seems to be restricted to one client, right? Because if you have there's no extension to multiple clients.
Yeah, so for now, we only consider a single client because you cannot have two clients that stores the stash consistently. So for now, we only consider a single client solution.
Okay, thank you.
Okay, do we have other questions? We have time. Great.
Thank you for the presentation. I'm new to this topic, but I may ask a very stupid question. As see on this slide, the server remove the data point from the address. So will it be the case that the server know which data has been retrieved by the client?
What do you mean by which data? So in this case, all of the documents themselves are encrypted.
Oh.
Yeah, so they're only going to see the addresses. Since the address is only being accessed once and never used again, the server doesn't learn any information from that.
So the server will see everything as like random bits?
Yeah, exactly.
Okay, thank you.
Okay, cool. We have more questions. Great.
I'm also not working in this research area, so it might be a dumb question. So I wonder if you possibly consider that the server also learns the amount of query results from the client. Do you plan to hide that information as well in your future work?
So do you mean query response volume?
Like 3 records, maybe contents Alice's query.
So in this case, we only consider a single client and single server. So there's only one single client, and you cannot. There's no two clients to distinguish from.
No, I mean maybe the server returns 3 data points.
Three data points.
Yes. In that case, a server learns that.
Yeah, the server is going to learn the volume leakage. That's what we call the volume leakage. But in our case, we actually have a countermeasure against the volume leakage itself. It's a form of bucketization, and I invite you to read our paper.
Okay, thanks.
Thank you.
Thank you again for the talk. So.